So last time we discussed about the kind of protection problem, that is the application of definite time overcurrent relay for the protection of the distribution feeder. And now, what was the problem statement in that very case? The problem statement was that given the magnitude of the loads and the fault current at the buses, how to set the DTOC relay, that is definite time overcurrent relay, at bus A and bus B, so that the entire feeder gets the overcurrent protection and arranged as the primary and the backup protection. That is, this feeder will get the primary protection. This feeder will also get the primary. This bus line will all get the primary protection. This line will get the primary protection, and along with that, this line will get the backup protection. So that was the protection problem that we have discussed. Now, how to do that problem? Now, first step in designing the overcurrent protection. First of all, what we have to do, the step number first. Is it audible? Is it audible to you?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So step first, how you have to design this. Now, first step is to select the ratio of the CTs. First of all, we want the transducer. So first step is to select the ratio of CTs. That is, we will have this line, and then we have the CT which is connected to that, and primary turns of CT and the secondary turns of the CT. So as already we have discussed that the standard CTs that are available in the market, it is of 1 ampere and 5 ampere. So we have to select the turns ratio of the CT. Now let us suppose that turns ratio of the CT is N2 by N1, which is equals to I1 by I2. So this is known as this component is known as that is a CT ratio. And let us suppose that the ratio of the CT is 100:1, then it is the CT of 100:1. So it is the CT of 100:1. And finally, if we know the ratio, we can calculate the value of the I2 from that. I1 is actually the current that is flowing in this. It is a very large value, and I2 is the protection circuit. So finally, what we are getting the I2 is equals to this 100 divided by I1. So in this way, we will get the value of the current which is used for the protection circuit. So what we have to do, the first we have to select the ratio of the CTs and the secondary current of the CTs. In this case, we have the primary and the secondary current. Now, in this case, the secondary current of the CTs is decided by the rating of the relay coil. This secondary current, it is decided by the rating of relay coil, and the primary current in this case is decided by the maximum load to be carried by the CT primary, that is maximum load current. So for deciding the turns ratio of this CT, we have to take into consideration the primary and the secondary of the CT. Now, the primary of the CT, that is secondary of the CT, it is decided by the rating of the relay coil, let us suppose that we have used the rating of the relay coil as 1 ampere. So its secondary is decided accordingly, and the primary is decided by the maximum load current to be carried by the CT primary. Now, next, this is the first step. Now, next step which is used is to we have to do the setting of the relay. As you already know, the fact that we first write the step 2. Step 2, that is the pickup value of the relay. And step 3, operating time of the relay. And together, these are known as the settings of the relay. As we have discussed previously, the basic block diagram of that, in that we have the value of the current, then we have the time setting, and then we have the pickup value. That is the pickup value of the relay. So we have to take into consideration these factors. Now, first is already over, that is the ratio of the CT that we have decided. Now, the second is the pickup value of the relay. So how to decide the pickup value of the relay? Now we will discuss the step second. Now, we decide the pickup value, that is the current value of the relay, taking into consideration the fact that the relay should allow the normal load as well as the certain degree of overload across it. That is, it can carry the normal load and certain degree of overload. Certain degree of overload, let certain degree of overload is 25% of the overload it can carry. So it depends upon the type of application. So it can carry, the pickup value is selected in such a way that it can carry the normal load and the certain degree of the overload. And so it means that it has that is, this value is more than the allowable maximum load. That is, whatever the maximum load which we are allowing, it is, this setting should be more than that. So that first thing we have to take into consideration. Second thing that we have to take into consideration is that was the first thing. Now, second thing that we have to take into consideration is that the relay should be sensitive enough to respond to smallest fault. That is, it must be sensitive enough to respond to the smallest fault. So it must be sensitive enough to be to respond to the smallest fault. It means that the setting of the relay should be less than the minimum fault current. It should be less than the minimum fault current. Let us suppose that we have the fault current, this minimum fault current. So setting should be less than the minimum fault current. And finally, we can say that the setting of this pickup setting of the relay should lie between IL max. It should be greater than this one, IL max. This is the pickup value of the relay, and it should be less than IF minimum, that is minimum fault current. So this rule we have to take into consideration while deciding the setting deciding the pickup setting of the relay. Now this can be explained with a simple diagram. Now let us suppose that this is the load current. This is the load current. This is the permissible overload. Let us suppose that load permissible overload, which is permitted, is 25%. And this is the minimum fault current. And this is the setting of the relay. That is, the setting of the relay should be decided in such a way that it should be greater than the maximum load current and it should be less than the minimum fault current as per this criteria. So this is the this is for the pickup value of the relay. So this is for the pickup value of the relay. Now, second is how to set the operating time of the relay. Now we have discussed the pickup value of the relay. Now we discuss the operating time of the relay. So how to decide the operating time of the relay? This is the third step that we have discussed. Now, there are certain principles which are used for the setting the operating time of the relay. So it is based on the fact that this operating time of the relay is selected based on the fact that the relay must get the adequate chance to protect the primary zone of protection, to protect its primary zone, and if the primary protection does not clear the fault, then in that very case the backup protection will initiate the tripping. So it will protect the primary part, and if it does not initiate, then the backup protection starts tripping. This can be explained by this diagram. If you see in this diagram, this you have seen that relay B is used for the protection of B and C, and A is used for the protection of A and B. Now you will see that this provides the primary protection. Relay B provides the primary protection to B and C, and this relay at A, it provides the primary protection at A and B, between A and B. However, this relay A also provides the backup protection to this feeder, that is to this line, that is B and C. So this relay RA also provides the protection to B and C, that is the backup protection, if our protection system RB does not initiate. Now this is so what we have to do, we have to select the time in such a way, operating time in such a way that if this relay does not operate, then finally we have the backup relay, it will protect the system. So we have to discuss this. Now, as we have already discussed that the operating time of the relay, we have to take into consideration the fact that it will protect its primary zone However, if it is desired for protection as a backup protection, then definitely it will provide the backup protection for the other zone also. Now, as we have discussed in the previous lectures, that as the fault takes place, it is sensed by both primary as well as the backup protection. Let us suppose that we have here protection system, then another protection system is here. Now let us suppose that it is B and it is A, relay A, and this is relay B. Now let us suppose that fault occurs in the system, then it is sensed by both RB as well as the RA. So it is sensed because this RA is also the backup protection for this system, for this line. So it is whenever the fault occurs, it is sensed by both RB as well as the RA, and it is the primary protection which will first operate. It is the primary protection which will first operate. So this primary protection will first operate for RB, and its operating time is less than that of the its operating time of A is less than that of the operating time operating time of B is less than that of the operating time of relay A. So that's why the selectivity is maintained if the operating time is less. Now, so what we have to take into consideration? We have to take into consideration that the operating time of this B is less than the operating time of A. However, when A operates, so whenever the A operates, A will give the signal to the circuit breaker. So there is some operating circuit breaker time also there. And then some, because of the electromechanical systems, we have some kind of overshoot is also there. So that thing we have to take into consideration. So some kind of overshoot is also there. So operating time of this relay A, then the operating time of the circuit breaker, which gives the signal to it, plus the this overshoot time. So we can say that this it is not for A, it is for B. So operating time of this B, then we have the circuit breaker time of this B, and then the overshoot time. So this operating time of A, this one should be greater than the sum of the operating time of B, operating time of the circuit breaker, plus the operating time of this overshoot. Now this can be explained by this small diagram. Now this is let us suppose that this is the relay operating time RB. So this is the relay operating time RB. Then we have the circuit breaker time, that is CB, circuit breaker time, and then we have the overshoot time. So some overshoot time is there. So relay this RA should be greater than this operating time of B, operating time of plus operating time of circuit breaker, and this overshoot time. So this is the rule that is to be followed. So it means the overshoot is due to the fact that it is due to the primary relay. So there is the proper coordination between the primary and the backup. So overshoot time in this case is defined as the time for which the relay mechanism continues to move even after operating coil has been de-energized. Relay mechanism continues to move even when operating coil has been de-energized. Even when or after operating time has been de-energized. Operating time has been de-energized. So, and this overshoot is because of the moment of inertia of the moving system. So this is due to the moment of inertia of the moving system. So this is due to the moment of inertia of the moving system. Now, in the light of the above discussion, we can say, that the correct procedure is to start the designing the relay or the setting the relay from the tail end of the feeder. So we start the setting of the relay from the tail end of the feeder, because in that very case the time is least. Start the setting of relay from tail end of the feeder. What it means? It means that we have the relay A here. We have the relay A here. Then we have the relay B here. So we start the setting from this relay. That is this relay. That is the tail end of the feeder. Because you can see, as we have discussed already, that this relay RB is made to can be made to operate without any delay. So it does not have to coordinate with any other relay. It does not have to coordinate with any other relay. Though this RA has to coordinate and it has to take into consideration the time of RB, circuit breaker of RB, and the overshoot time. So we start with the setting of the relay RB. Now let us assume we have to assume some numerical values. Now let us assume that the operating time of RB is 0.1 second. That is T RB is equals to 0.1 second. It means that it has the least time. Then let us suppose it means that this RB has to wait for 0.1 second it has to wait for 0.1 second to operate. Now let us suppose that this R, as we already know the fact that T RA is equals to T RB plus T circuit breaker time at B plus overshoot time. So let us suppose that it is 0.1 second that we have here written. Then let us suppose that circuit breaker time is 0.5 second, and let us suppose that overshoot time is 0.2 second. So total time setting of the relay A, relay A to operate is equals to the sum of these. So it is 0.8 second. So it means that time setting between the operating time of two relays, time setting between the operating time of two relays equal to the sum of the operating time of circuit breaker at B and overshoot time of the relay A. And this is essential for maintaining the selectivity. This time is essential for maintaining the selectivity between A and B. So it is essential for maintaining the selectivity between A and B. So it is also known as the selective time interval, that is STI. So it is also known as the selective time interval. So between the time interval of A and B, there is the selective time interval. So that selective time interval we have to take into consideration. Now, from this whole of the discussion, you have seen that setting started at the tail end of the relay. Setting started at the tail end of the relay because it doesn't have to coordinate with any other relay, and it is the fastest one. And also this started due to the fact that no coordination requirements are there and time is also less, and it is not constrained by the selectivity problems. This relay is not constrained by the selectivity issues. It is not constrained by the selectivity problems. However, all other upstream relays upstream means that we have in this case relay A. It was the downstream because it was the feeder, and it was the radial feeder, and we have the generator here, and this is downstream and this is upstream. So all other upstream relay are tied up with the downstream neighbors. So all other upstream relays are tied with downstream neighbors. So also one more point we have to take into consideration, the fact that as the fault moves towards the source, the fault current becomes longer. That is, let us suppose that here we have the source. We have here, let us suppose ZS, then we have the line, let us suppose ZL, and let us E. Now the current you will see in this case is E divided by ZS plus ZL. Now, when we are moving towards the source, ZL is decreasing. When we are moving towards the source, it means that this impedance is decreasing. So ZL is decreasing, and as a result, the current is increasing. It means that if let us suppose that it is a fault current, then as we are moving towards the source, the fault current becomes larger due to the fact that this impedance is reducing. It is removing from the, it is getting smaller and smaller. And as the fault current is, this fault current becomes larger, and the fault clearing time also become fault clearing time also become longer. Now this is due to the fact that relays near the source, relays which are near the source are deliberately delayed because they are selective with the relay downstream. So because of selectivity issues, the relay near the source are deliberately delayed. Because they are tied with the upstream relays. Here they are tied with the downstream relay, and they have selectivity issues that is taken into consideration. So this is not desirable. This is not a desirable future. This is not desirable. However, it can be shown that the significant improvement in fault clearing time is can be obtained if we use the IDMT relay. That is, significant improvement is obtained in clearing time is obtained if we are using the IDMT relay. So IDMT is the inverse definite minimum time relay. Inverse definite minimum time relay. So this is about the DTOC relay. Now we can do the setting for this inverse definite minimum time relay. Now the whole of this is explained with the help of a small diagram. In this case, you will see that the fault current increases as we are moving towards the source. And in this case, this is the STI, that is the selective time interval. And then we have the RB, that is the operating time of the relay A. And this is operating time of the, operating time of relay B. And this is the operating time of the relay A that we have discussed. This is in case of the DTOC relay, that is definite time over current relay. Now, we can discuss the setting for inverse definite minimum time relay for the distribution feeder. Now, while explaining this, we have to discuss a small problem, and then that problem will give you an idea that how we have to do the setting of that type of relay. So next is the application of inverse definite minimum time relay. For the protection of, and that is on distribution feeder, or for the protection of the distribution feeder. On the distribution feeder. Some of the formulas that you have already discussed, and we have already discussed, that are used in that. First, that is turns ratio formulas that we use for this setting. That is, we have discussed previously. That is N2 by N1 equals to let us suppose it is I1 by Y2. So this is the CT ratio, N2 by N1 is the CT ratio, and finally we are getting I2 as the I1 divided by this CT ratio. Let us suppose it be A. This first formula, it is used. Then we have to calculate, we have to use the formula of PSM that we have discussed in the previous lectures also. That is the I relay, that is current across the relay, which we are getting out of that. And then we have the flux setting. What is the setting of the particular relay? Now, third formula that we have to use is in case of this IDMT relay. In case of IDMT relay, the operating time of the relay is given by, let us suppose that operating time of the relay B, it is given by the expression 0.14 time multiplied setting TMS into divided by PSM raised to power 0.02 minus 1. So for the setting of the relay, we have to use certain relations, and these relations we have already discussed in the introductory chapter, since it is an inverse definite minimum time relay. Now, this is the problem that we have to discuss. In this case, you will see that it is a feeder, radial feeder with the two buses A and B. It is a radial feeder. We have the two buses A, B in that very case, where we have installed the IDMT relays, that is relay A and relay B. Now, it should be noted that the purpose of the relay B, this one, is to provide the primary protection to BC. So this relay will provide the primary protection to BC. And relay A, as we have discussed in the previous case, relay A will provide the primary protection to section AB. It will provide the primary protection to section A and B, and it will provide the backup protection to this section also. That is, relay A provide the backup to this section also, that is B and C. So this problem we have to discuss in relation to the definite minimum time relay. So as we have discussed in the previous case, we start with the tail end of the relay. It is the rule of thumb, that is, we start with the tail end of the relay. It's a very beautiful problem. When you will do this problem and you understand this problem, then definitely you will be able to do the setting of the relay of your own. What we can do in this case, we can do the setting with the maximum load current, and that is maximum fault current. In this case, maximum and minimum fault current is also given. That is, IF minimum, IF maximum is 3500 and 4000 ampere. Then we have IF minimum and IF maximum at the bus B is 2000 and 3000 ampere. And then at the bus C, we will have this minimum is 1000 and the maximum is 1500 ampere. So we can do the setting for the maximum value of the this fault current, and we can check whether that setting is good with, we can test with the minimum value, and if the time is within that range, it will trip, then definitely our setting is perfectly fine. So that thing we have to take into consideration. Now, as the rule of thumb that I have discussed, that we will start from the tail end of the relay. We will start the setting from the tail end of the relay because it has no selectivity problems and it doesn't have to coordinate with any other relay. So we have to discuss this one. Now, first, how it starts. The first step is decide the CT ratio and the plug settings. Decide the CT ratio and plug settings, which is obviously for the tail end of the relay, that is relay B. Now in this case, you will see first we calculate the maximum load current in this case. First we calculate the maximum load current. As we have discussed in the previous case, the maximum load current, we can allow some overload. That is, the setting of the relay should be such that, that is plug setting of the relay should be such that it will allow some overloading. That we have assumed at that very time, that is 25%. Now, at the relay B, you will see that what is the, at the relay B, so what is the load current? Now, in this case, the load current, it is scattering this one, it is scattering this protection system. So in this case, it is 80 amperes. So maximum load current taken into consideration, the overloading also is equals to 80 plus 25% of 80, means we allowed the 25% of overloading into 80, and finally it is 100 ampere. So the maximum load current in this case is 100 ampere. Now, let us assume that 1 ampere relay is used. Let us assume we have used the 1 ampere relay, and as per this, the CT ratios would be 100 is to 1. 100 is the maximum load current, so the CT ratio would be 100 is to 1. It depends upon the maximum load current. Now, let us suppose that plug setting is done at 100%. Plug setting is done at 100%. It means that plug setting is 100%. It means that it is 1 ampere. This is in case of relay B. So we have to calculate the maximum load current. Then we assume the 1 ampere relay is used for the at the secondary end. That is for the protection circuit, and the CT ratio would be 100 is to 1, and plug setting is 100%. So plug setting is 1 ampere. So that is for the relay B. Now, for the relay A. Now we have to do the setting for the relay A. This is 1. This is second. So at the relay A, we have to see at now. What is the total current that is taken into consideration at the relay A? So at the relay A, it is used for the protection of this one and this one. It means that the total current in this case is 160 ampere plus 80 ampere, because it is also providing the backup protection for this feeder. So for the A, we will have the 160 plus 80 ampere. So maximum load current in this case is 160 plus 80 and 25% of overload, as we have done in the previous case also. So it is 25% of overload. So finally, we are getting the value is 300 amperes. So it is 300 amperes. So sorry for the interruption. So in this case, you will see that the maximum load current is 300 amperes. Now, as we have done in the previous case, let us suppose that 1 ampere relay is used. Let us suppose that, let us assume one ampere relay is used. So as we have done in the previous case, the CT ratio in this case would be 300:1. So it is the CT ratio. Now, as we have done in the previous case, the plug setting is 100%. It means the plug setting value is 1 ampere, as we have done here. So these are the sum of the values that we have calculated. Now we discuss the time multiplier setting, TMS. So time multiplier setting, as we have done in the previous case, we start with the remotest relay. That is, in this case, the remote relay is RB. So we start with the relay RB. Now, in this case, as we have discussed previously, that since the relay RB in this case, it doesn't have to, it doesn't have the selectivity issues because it doesn't have to coordinate with other relay. So this relay RB, it does not have to coordinate with any other relay, and it can be made to operate fastest. It can be made to operate fastest. So let us suppose that TMS of this relay at B is selected as TMS of the relay B is taken as 0.1. Time multiplier setting is 0.1. Now, as we have discussed previously, in order to maintain the selectivity between the two relays, we have to take into consideration the fact that the operating time of the relay A is equals to operating time of relay B, operating time of relay A for maximum fault at B. Is equals to the operating time of B for maximum fault at B plus circuit breaker operating time at B plus overshoot time. So that thing we have to take into consideration that we have already discussed. Now we have to calculate the operating time of RB. Already TMS in this case is given as 0.1. So we have to calculate the operating time of B, and as per the relation that we have discussed previously, the operating time of this type of relay, it is given by 0.14 TMS divided by PSM raised to power 0.02 minus 1. That we initially.
सर हेलो सर.
हाँ बताओ
सर प्रीवियसली सर आपने शो की थी रिलेशन 0.5 इंटू TMS IDMT रिलेज के लिए.
कितनी
0.5 TMS डिवाइड बाय PSM. सर नीचे सेम है 0.14 की बजाय, मतलब प्रीवियसली जब आपने पहले क्लास दिया था.
एक मिनट
सर इधर नहीं सर, मतलब कि जो इससे पहले आपने क्लास में दिखाया था.
अच्छा, जो मैंने बताया था तुम्हें.
यस सर, वहां पे आपने दिखाया था IDMT रिले में
0.14 होगा.
अच्छा सर ठीक है. फिर सर वहां पे
डिफरेंट टाइप ऑफ रिलेज थी ना
सर. IDMT रिले था ना वहां पे, ये भी तो वही.
एक मिनट मैं अभी देख लूं, मुझे लगता है वही होगा. नहीं यही है रिलेशन. 0.5 किसके लिए है? नहीं, एक तो ये वाली रिले है, उसके बाद वेरी इनवर्स रिले है, उसके बाद एक्सट्रीमली इनवर्स है. तो जो ऑपरेटिंग टाइम ऑफ IDMT रिले है वो यही है 0.14 TMS PSM 0.02 माइनस 1. यही रिलेशन है.
ठीक है सर, मतलब वहां पे मतलब होगा कुछ.
नहीं वही यही
गलती हुई.
रिलेशन.
ठीक है सर, ठीक यही है सर.
ठीक है. तो अब हमारा आ गया ये RB 0.14 TMS PSM raised to power 0.02 minus 1. Now, what is the maximum fault current at the B? So from the figure, you will see from this diagram, you will see that what is the maximum fault current at B. So the maximum fault current at the B in this case is 3000 ampere on the primary side. So हम क्या करेंगे? What we have to do? We have to do the setting for the maximum fault current. So in this case, the maximum fault current for the B is 3000 ampere. And if the maximum fault current on the primary side is 3000 ampere, that is maximum fault current at B, it is equals to 3000 ampere. Now, we have selected the ratio of the relay as CT, ratio of the CT as 100:1. So on the primary side, this is actually on the this secondary side. This is on the primary side, that is the maximum fault current of 3000 ampere. It is on the primary side, and on the secondary side, the current becomes, because the CT ratio we have chosen as 100, in this case in the relay B we have chosen as 100:1. So it is 3000 divided by 100. So it is 30 amperes. So it is the maximum fault current, and it is on the secondary side. The fault current is and this 30 ampere, because CT ratio we have chosen as 100:1 in this case. Now, this is actually the current which is seen by the relay. So we will have the PSM is equals to I relay divided by plug setting. Plug setting we have chosen as 1 ampere, 100% in this case. And I relay is the current which is seen by this particular relay. It is the secondary fault current. That is, what is the fault current which is reflected on the secondary. So finally, we are getting the PSM of 30. So we are getting the PSM of 30. So PSM in this case is 30. Also, we have set here initially, we have set the TMS, time multiplier setting of the relay as 0.1. So we have set the TMS as 0.1, and we have set this is PSM, its value we calculate it is 30 from here. That is what we do. We get the maximum fault current, we reflected it on the secondary side, and secondary side whatever is the fault current is the current that is seen by the relay. So PSM is I relay divided by the plug setting, and plug setting is 100%, it is 1 in this case. So we have 30. So finally, the operating time of the relay RB is obtained by substituting these values, and its value is approximately 0.2 seconds. So we got the operating time of the relay RB. We start with the relay RB because it is at the tail end. So operating time of the relay RB is equals to 0.2 seconds. So RB, we take it as, we calculated it as 0.2 seconds. Now, second, the circuit breaker time of B. Circuit breaker time of at circuit breaker B, and let us suppose that circuit breaker time is 0.5 seconds. So finally, the relay time and the circuit breaker time of B is equals to 0.7 seconds. So total time is 0.7 second. It is the desired, it is actually the desired operating time of RA. However, we can say that it is the desired operating time of RA. However, as we have discussed that one more factor that is coming into this is the overshoot time. We have also taken into consideration, we have to take into consideration this overshoot time, and it is the rule of thumb that we have to take the overshoot time, the 10% of this one. It means we have to take the overshoot time as 10% of this value. So finally, the overshoot time we are getting as 10%, which is equals to 0.07 seconds. So the operating time of RA. So finally, we are getting this operating time and then overshoot time. So finally, the operating time of RA for maximum fault at B. For maximum fault at B, bus B. We have taken here the maximum fault current. So the maximum fault at B, so it is given by P RA this time to 0.5, that is 0.2, 0.5 plus this one 0.07, and finally we are getting 0.77 seconds. So this is the operating time for A for the maximum fault at B, since we have assumed the maximum fault in this. We have taken the maximum fault current in this case. Now, in this, we have calculated the TMS. We have calculated the TMS time multiplier setting of B and the plug multiplier setting of B. Now, to complete all the specifications, we have the operating time of A that we have calculated. It is the operating time of B, but we have calculated the operating time of A. And we want to know about the TMS and PSM of the A, because the setting is complete when we have the CT ratio, when we have the plug setting, and when we have the time multiplier setting. So that setting is the main setting. We have to complete it. So we know the operating time now of A. We know about the operating time of A. Now, as per the expression, this operating time of the A, TRA, as we have discussed, it is equals to 0.77. Operating time is equals to, for IDMT relay, is 0.14. TMS divided by PSM raised to power 0.02 minus 1. So this is already, we have to calculate the TMS and PSM only then our whole of the setting of the relay is complete. Now, we know that the PSM is equals to, we know that PSM is equals to current seen by the relay, that is the secondary current of the CT, and plug setting. And the plug setting in this case, we have taken as 100%. So its value is 1. Now, what is the value of the I relay? Now, since we have taken the maximum fault current as 3000 ampere, we have taken the maximum fault current as 3000 ampere, and the CT ratio we know. In this case, the CT ratio in case of A is 300:1. Finally, we are getting, this is on the primary side, and on the secondary side, we will have the 3000 divided by 300. 3000 divided by 300, which is coming out to be 10. So this 10 is actually this one. So finally, we are getting the PSM as 10. So plug setting multiplier we get as 10. Now, we know the value of the plug setting multiplier. Substituting the value of the plug setting multiplier in this as 10, we get the value of the time multiplier settings. While substituting the value, we got the value of the time setting as 0.26. So this we sets the finishing of we sets the relay, or we can say that we finishes the setting of both the relays. So we can explain it, that is we can do it with a table. Now in this case we have the relay, then in the second we have the CT ratio, then we have plug setting, that is PSM, and we have TMS, time multiplier setting. Now we have the relay RB, then we have the relay RA. We have the relay RB, then we have the relay RA. CT ratio in this case is, in the relay RB is 100:1. In relay RB, it is 100:1. In relay RA, it is 300:1. Then plug setting is 1 ampere. It is not plug multiplier setting, it is only plug setting. So it is 1 ampere, and it is 1 ampere, 100% we have chosen. And time setting that we have calculated, in this case it is 0.26, in the second one 0.26, and in the first one we have calculated RB is 0.1. So this is the table for the relay settings and various values that we have calculated for the maximum value of the fault current at B. Now this we complete the setting of the relay. Now we have to verify the selectivity for the minimum fault current. We have done the setting for the maximum fault current. We have done our setting for maximum fault current at B. Now, what we have to do, we have to verify that the selectivity for the minimum fault current is maintained or not. It should be our setting is perfect, or this setting is perfect. In that very case, the setting is maintained, the selectivity is maintained. However, it is not perfect, then definitely we have to go for some other setting. Now, as we have seen, in this case, the minimum fault current at B. we have done the setting for the maximum fault current and we have done the testing for the minimum fault current. Now, what is the minimum fault current? In this case, the minimum fault current is 2000 ampere. So minimum fault current is 2000 ampere at the bus B. Now we have to check whether the selectivity for the relay A is maintained or not by using these settings. Now, these settings we have to use. We have to use the TMS and plug setting, this only, and same CT ratio. So we have to do the verification. Now in this case, you will see the minimum fault current at B. So minimum fault current at B is equals to 2000 ampere. Now relay B current corresponding to this, that is secondary current of CT. Since in case of BT, in case of relay B, this CT ratio is 100:1. So finally, it is 2000 divided by 100, which is equals to 20 ampere. This is the relay current, that is the current seen by the relay. This is the relay current, and as you already know, the PSM in this case is equals to the plug setting multiplier is equals to I relay divided by the plug setting. Plug setting is taken as 1 in this case, so it is 20. So PSM is 20. And for the relay B, that we have assumed that time multiplier setting as 0.1. It is 0.1. So PSM we calculate. TMS is 0.1. Now substituting this value in the formula, we will get the time for operation of the relay B, that is TRB for minimum fault at B, which is equals to TRB 0.14 into TMS 0.1 divided by 20, PSM is 20, 0.02 minus 1, which is equals to 0.226. So this TRB is equals to 0.226. Now, circuit breaker time that we have assumed in the previous case is 0.5 seconds. So TCB circuit breaker time for the minimum fault at B is equals to 0.5 second. Now, as we have done in the previous case, this expected operating time of this RA should be greater than the sum of 2 plus 10% of this sum of 2 to take into consideration the overshoot. So expected operating time of RA is equals to, it should be greater than the sum of the two, that is 0.226 plus 0.5 plus, to take into consideration the overshoot, we have to do the 10% of that. So 0.226 plus 0.5. So finally, we are getting it as 0.8 second approximately. So its value is 0.8 second approximately. So the value, expected value of RA, it should be greater than 0.8 seconds so that the selectivity is maintained. Now, this is the expected operating time of RA taken into consideration the fault at B. We have to calculate the operating time of B, then we have to calculate circuit breaker time, and then we have to take into consideration the overshoot also. So this is the expected operating time of RA. If our relay will trip, then the actual operating time of RA should be greater than this value, that is 0.8. If our system would be perfect, if the relay will operate. Now, we have to calculate the actual operating time of RA. So, how to calculate the actual operating time of RA? That procedure, the same procedure that we have followed for RB, that is the minimum fault current. Fault current minimum at B. Since we are doing the protection for B, so fault current minimum at B is 2000 ampere. Then the current, the secondary current corresponding to this is the fault current. So secondary current, which is also equals to current relay corresponding to this, taken into consideration the turns ratio, and in this case the turns ratio is 300:1 in this RA. So we will get the I relay as 2000 divided by 300. So we are getting 6.66 ampere, and we are getting the PSM as I relay divided by plug setting. Plug setting we have taken as 1, so it is 6.66. So its value is 6.66. Now, the plug setting is 1 ampere, and this PSM we get 6.66. Now, for the relay RA, we have the value of TMS. What is the value of TMS? From the table, for the relay RA, we have the time multiplier setting as 0.26. So using this in the formula, we get the operating time. So finally, the TRA for the minimum fault at B is equals to, let us suppose that is given by TRA. So it is given by 0.14 into TMS that we have calculated, 0.26 from the table, 6.66 PSM, 0.02 minus 1, which is equal to 0.94 seconds. So this is the operating time of the relay A for the minimum fault at B. Now, what value we got for this is the actual value that we got, and this is the value that we got from by solving at the relay B. So it means that actual value that we got is equals to 0.94, and it is greater than this value 0.8. So it means that our selectivity between A and B is perfectly maintained. That is, we have maintained the perfect selectivity between the two, and as a result, the results that are listed in this table are perfectly all right. So the results that are in the table are perfectly all right. So this is how the setting can be done. We have done the setting for the maximum fault current, and then we check that with the minimum fault current and see whether the selectivity is maintained or not. So this is the perfect setting for this type of relay. Now, the certain points that we obtained from this is that certain points that we obtained from this is that first point is that we start from the tail end of the relay. Start from the tail end of the relay setting. We have to start from this tail end of the relay, and the plug setting should be greater than the maximum load current, and it should be less than the minimum fault current. It should be less than the minimum fault current. And third point, the TMS should be decided such that TMS should be decided such that selectivity with the next relay downstream is maintained with the maximum fault current at the beginning of the next section. So TMS should be decided so that the selectivity is maintained. Now, whole of this values, whole of these results are, these are summarized in one diagram. So these are summarized in this one diagram. Here you can see that this is the selectivity is maintained between RA and RB. RB is this is the curve of RB, that is relay RB, and this is the RA, and this is the time for that, and this is the selectivity between the two. So in this phase, the selectivity is maintained. And however, if you see in this case, we have two buses only. We have three buses in this case, and two line sections are there. However, if we have the n bus system, then for that we can have the computer. We can make a computer algorithm to automate the task. So we can have the computer algo to automate the task. This we have done for the 3-bus system, and the 2 lines are there in the system. So if it is more than that, then in that very case, we can automate it by using some algorithm that we have discussed, and that algorithm can be used to automate that particular task. So this is all about the this system. This is all about the setting of the relay. Here we have the whole of the system is given. We have the minimum and the maximum fault current, then at A and then at B. So here whatever is given in the it is given in the table. Here it is summarized in the form of the figure. So if the computer program is given, definitely if we have to do it for the inverse system, definitely we can make the computer program for that. So anything related to that, if you want to?